Can dark energy be overcome by the Great Attractor? The vastness of the universe is accompanied by its beauty. When a tiny, dense fireball exploded 13.8 years ago, the universe was created. Everything we know of originated in an infinitesimally small singularity, a point of infinite density and infinite heat, according to the Big Bang hypothesis, our best and most widely accepted explanation for how the universe came into existence. The universe is still expanding today. In comparison to the age of the cosmos, we humans have only existed for a relatively small portion of that time. Still, we have seen a lot of things and have a lot to learn about the universe's mysteries. The Hubble Deep Field is the best illustration of how much we can see and that there are more powerful forces at work in the cosmos. Gravity and dark energy are two such factors, both of which are extremely important for the future of our universe. In this video, we'll discuss the Great Attractor, a peculiar location in the cosmos that seems to be drawing everything there. The cosmos is growing at an increasingly rapid rate on its biggest scales. This sentence has a significant impact on our future. Due to the gravitational attraction of all stuff in the cosmos, scientists in the 23rd century assumed that the universe's expansion had to slow down. But Hubble was perplexed when he pointed his telescope up towards the sky. He saw that a galaxy moved away from us more quickly the further it was from us. Nobody expected this result to come to this. What might be the cause of this phenomenon? In the end, scientists discovered an unseen force that accounts for 70% of the universe and is in charge of pushing far-off galaxies apart over time and causing them to speed up from one another's perspective. But because matter tends to clump together in our own galaxy and local group, gravitation can prevent the expansion of a region if a sufficient amount of matter gathers there. However, we are aware of larger structures besides galaxies and groups. Galaxies can be found in both clusters and superclusters throughout the universe, some of which are even nearby. Will one of them ultimately be able to defeat bad energy? Numerous thousands of galaxies are pulling on us all the time. Will they ultimately manage to entice us in spite of the dark energy? Or will dark energy cause us to grow swiftly enough to avert that? Three things must be taken into account in order to answer this question: the universe's expansion, regional defects in that motion, and how the universe seems to us. The universe's expansion. As was already mentioned, Hubble's observations in 1920 perplexed every scientist. Hubble developed Hubbles Law, which specifies the rate of galaxy retraction from Earth. Edwin Hubble was able to recognize a well-known class of stars, Cepheid variables, and the spiral-shaped objects he saw in the sky. They appeared to periodically grow and dim throughout time, with each star having an inherent lifespan. These stars all have a brightness/time period relationship, which means that if you can measure that time period and their apparent brightness, you can figure out how far away each star, and consequently the galaxy it's in, is from you. We have gone from Cepheids through other galaxies to Type Ia supernovae as the brightest, most recognizable standard candles now in existence. By using these techniques, we've discovered a relationship known as Hubble's Law, which states that the apparent speed of an object moving away from us is proportional to the Hubble parameter times the object's distance. You may have heard it referred to as the Hubble constant, and it was a useful way to conceptualize it in the years and decades prior to the Hubble Space Telescope because, at the time, we had only seen around halfway across the universe. However, the more we looked, the more we noticed that the expansion of the universe was not only changing through time, but was also accelerating, suggesting that there was more to the universe than just matter, radiation, and curved space. Instead, the dark energy that makes up roughly 70% of the universe today is becoming more and more important. Because dark energy made up such a small portion of the total energy density 500 million years ago, it was not detectable. However, as the universe expands, dark energy takes control, producing the acceleration we observe today as matter and radiation saturate and lose density. It follows that no structures in our universe will ever be bound together by gravity if they are not already gravitationally connected and have not significantly increased in density. Instead, they would move faster in keeping with the universe's expansion. Local imperfections in the universe's movement. Gravitation had plenty of time to play a part in the creation of the universe, even when we consider it on larger scales of millions of light years. The universe's large-scale structure became rich and complex in the first few billion years following the Big Bang, resulting in the formation of trillions of star clusters and hundreds of billions of galaxies. The most dense regions grew not merely into galaxies, but also into groupings and clusters of tens, hundreds, or thousands of galaxies, all bound together in one huge region. The gravitational pull of these faults is quite crucial. We are 2.5 million light-years away from a galaxy like Andromeda, our nearest neighbor, when we stare out at it. Based on the universe's expansion, it ought to be moving away from us. However, if these two galaxies are massive enough, the gravitational attraction of the Milky Way on Andromeda and of Andromeda back on us in the Milky Way can offset the expansion. We'll become gravitationally connected together if the attraction force between them is large enough, and it was large enough early on. Although dark energy may push other galaxies away from us, we will eventually merge and fuse into a single gigantic structure throughout time. This is going to happen. This is how our local group actually ended up. To answer Bob's question, we must first determine what is happening with the Great Attractor and the nearby clusters and superclusters. We must first map out the nearby, local universe before we can do it. But one thing is sure, on smaller scales of galaxies that are nearby, gravitational force wins over dark energy. As the Hubble law itself indicates, the farther away a galaxy is, the faster it is retreating away from, as on longer distances dark energy prevails. We have discussed the universe's overall size and its expansion. We have also discussed the regional flaws. Let's examine the local universe to see what it looks like. Over 80% accuracy is what we've achieved here. The areas we've missed are the galaxies positioned behind the galactic plane, which are impossible to detect from our vantage point. We can consider three things concurrently: the motions of each unique galaxy in our proximity with respect to us. Galactic distances and Hubble's expansion of the universe can be used to determine how far these galactic motions depart from Hubble's law. The masses of everything we can observe and deduce, as well as the masses that must exist at specific points in the universe in order to produce the motions we notice. As a result, we map the local universe's position, velocity, and mass while also seeing how and why objects move. This aids in our mapping of the immediate universe. All of this information was recently compiled by the Cosmic Flows Project, which found that the Milky Way is a member of the local group, that our group is one of many nearby but outside the Virgo cluster, and that all of these groups and clusters together with a few others make up the Laniakea supercluster. The missing mass was formerly known as simply as the Great Attractor, since the motions we observed did not match the masses we discovered, yet it must exist in order to explain the motions of these local structures. The local group and numerous additional galaxies in our local supercluster are drawn to this mass by the extremely large structure, the group of galaxies in Laniakea, that generates this powerful, alluring attraction. They diverge by hundreds of km per second from the Hubble flow. It's a real force with a big impact that works against dark energy and the Hubble expansion. But it falls short. It is obvious that the attractive pull of dark energy in the universe's current expansion is more powerful than that of the nearby supercluster. Only around 20% of the anomalous velocity or divergence from the Hubble expansion is required to connect us to this enormous object. In reality, the structure isn't truly restricted. Laniakea is just an apparent structure that will disintegrate as the universe expands. The Great Attractor, or Laniakea, is where we are being drawn, therefore the answer to the big question is that we are being drawn there, but the force that is drawing us there is pitifully insufficient to cause us to fall in. It can only make the supercluster travel away from us a little more slowly than usual, staying within our reach for a few billion years longer than a galaxy on the other side of the sky that is equally distant. Although authentic and large, Laniakea is nevertheless fleeting and lacks sufficient size to hold itself together or ultimately ensnare us. After all, the fate of our little group is a lonely one. But what do you think will happen to our neighborhood group? What role does dark energy play in our universe? Comment below with your thoughts and let us know what you think.